Hello, my wonderful AP Chem students. As I've been talking to a few of you and you've been prepping for the exam, there was a couple of things that I wanted to point out and work on with you that you seem to have some questions on. So first is our acid base and then conjugate acid, conjugate base. And we're looking at the Bronston-Lowry model of this. So we have acids for our Bronston-Lowry is a proton donor, or like an H+ donor, and then bases are proton receivers. And as I'm pointing to them, I don't even know which one's which. So let's look at this. We have an NH4, and then that's going to turn into an NH3. So this is actually our donator, right? Like it's going to lose that hydrogen. So this is going to be my acid. And then we go CN minus, and then it turns into an HCN. So it took that hydrogen, and so this is going to be our base. Okay. Now the conjugate acid and conjugate base is on the other side, and it's what it turned into. So if this is NH4 and it lost the hydrogen, then that's going to be our conjugate base. So our acid will always line up with our conjugate base, and then our base will always line up with our conjugate acid. Okay? And when I'm looking at this, that's like the forward reaction, right? If we look at the reverse reaction, we see that our conjugate acid is what's giving up the hydrogen and our conjugate base is what's receiving it, looking at the reverse. All right, beautiful. Now we can identify which is our strong and our weak by either identifying strong acids or strong bases. The other way of looking at this would be if we had a K value, an equilibrium constant. So this one might be a little bit harder to know, and so if the problem provided you with an equilibrium constant, let's say hypothetically that K was less than 1, okay? So if it's less than 1, we're actually favoring the reverse reaction. So that means that we are not favoring this forward reaction very much. It's unlikely that this will dissociate into that conjugate base, or it won't readily do that. So if it doesn't readily dissociate, then this would be our weak acid. And then its conjugate base, that relationship means its conjugate base would have to be strong. Okay? And then think of it in the reverse as well. We said that we're favoring this reverse reaction. So that means this does dissociate rather easily. Like it is going to easily turn into this. So that would make this conjugate acid strong. And so then its base must be weak. So now we can compare the bases and the acids, right? So if I look at these two acids, well, this one's going to be my weak one, and this one's going to be my strong one. And if I compare the two bases, then this is going to be my strong base, and that's going to be my weak base. Okay, let's jump down here. We have a perchloric acid. Is that right? This is one of our big 6. It's a strong acid. Like we know already that it's strong. And it's an acid. And we see this because it gives up that hydrogen. So this must be the conjugate base, and it's going to be weak. Okay. So now we have our base that's going to receive, right? That's what makes it a base, is that it's going to receive. And so then this must be my conjugate acid. Okay. If we know that this is a strong acid, that it's readily going to dissociate into this, then we're going to be favoring that forward reaction, right? It'd be like K is greater than 1, or equilibrium constant is greater than 1. So we are favoring the forward reaction, meaning that this is going to readily dissociate into that. But it would also mean that this does not readily that's my acid. This one does not readily dissociate or give up a hydrogen to become this. So then that must be my weak conjugate acid, and then by that relationship of conjugate acid to base or acid to conjugate base, if this is weak, then that must be strong. Okay? And so now looking at these again, If I'm comparing my acids, then I would have this one's strong, that one's weak. So this would be my strong acid in this example, that would be my weak acid. And then comparing the bases, this would be my strong base, and that would be my weak base. Okay. Let's see how much time we got. Okay, we got some time. The other thing that I noticed that I had lots of questions on was redox reactions in an acidic solution. Okay, so I'm turning to that assignment right now. Reminder, the ones that I want you to finish are the acidic solutions ones. So it's like the first 4 questions I want you to do. Experimentally determine. Okay, so this one, this is a good one. I want to find one that maybe we have to identify. Let's look at number 4. So I'm going to assign my oxidation numbers. So we know our oxygens are going to be -2 charges, or oxidation numbers, and overall it's a -2. So we'd get like a +4 and a -2, and then they have -2, -2, -2. So -6 total oxygen, so this must be a +5 and a -2 on my oxygen. Okay, so now we have 4 of those oxygens, so total oxidation number for all the oxygens would be -8. So this must be a +6, -2, not a +2, -2. And then -2 +2. Okay, so my sulfur went from +4 to +6. So then that would have been oxidation. And then my nitrogen went from +5 to +2, so that'd be my reduction. So once I identify that, I'm going to write the half reactions. We'll start with our oxidation half reaction. So we have sulfuric, or not sulfuric, sulfite, aqueous, and that's going to result in sulfate, aqueous. It's already in its polyatomic ion, so I'm not disassociating it more than that, even though it's aqueous. And then similar to this is a gas, and then this is our nitrate that's already in its ion. So we'd have NO3 minus aqueous, resulting in nitrogen monoxide gas. Okay, so once we've gotten our half reactions, our second step is to balance the atoms that are not oxygen and hydrogen. So sulfur 1, nitrogen 1, nitrogen 1. So those are already balanced. Next, I'm going to balance the oxygens by adding water. So right now we have 4 oxygens and 3 oxygens. So I'm going to add a water molecule, so we have the right amount of oxygens. And then down here I have 1 oxygen and 3, so I'm going to add 2 water molecules. Okay, so that I can have 3 oxygens and 3 oxygens. After completing that, I'm going to add H pluses to balance the hydrogens. So I will have 2 H plus aqueous, and our waters are liquid. And then we have 4 over here, so I'm going to have 4 H plus aqueous. All right, nice. Now we need to balance the charges by adding electrons. So I have one thing that's neutral, and I have one thing that's a -2. So over here I have a -2. And then I have a -2, one thing that's a -2, and 2 things that are +1, so this would be 0. So right now we have 0, and then we have -2. So I need to add 2 electrons over here. Now I have 4 positive ones, and I have 1 -1. So I have a +3 going on, and then this is neutral. So then I need to add 3 electrons right there. Okay. Now that I've figured out the electrons, we need to have the same amount of electrons that's being produced as is being consumed. So this needs to be the same as that one, so I'm going to multiply everything by 3 and then everything by 2, so that it's 6 electrons both times. So this is going to turn into 6 electrons. okay? And then down here I'm going to multiply everything by 2. So now this is 6 electrons, 8 hydrogen ions, 2 nitrate, 2 nitrogen monoxides, and 4 water molecules. Once I have balanced all of that, then if it's showing up on the reactant side and the product side, it can cancel just like the electrons. But that might not be the only thing. Like I have 3 water molecules, and then there are 4 water molecules. So all of those are going to cancel, and then I'm going to be left with 1 water molecule on the product side. And then I have 6 H plus ions on the product side, and I have 8 on the reactant side. So all of those will cancel, and I'll be left with 2 H pluses. Okay, so that's everything that cancels. So now our total net ionic balanced redox reaction in acidic solution, and doesn't that sound fancy, would be 3 SO3 2 minus aqueous, and then 2 H plus aqueous, 2 nitrate aqueous, and that's going to result in 3 sulfate plus 2 nitrogen monoxide and 1 water molecule. Oh, as I write off the page, you can't see. Okay, beautiful. You can check your work by making sure that you have the same, that the atoms are balanced and the charges are balanced. So we have 3 sulfur, 3 sulfur. We have 9 plus 6 more, 15 oxygens, and then we have 12, 13, 14, 15 oxygens. We have 2 hydrogens, 2 hydrogens, 2 nitrogens, 2 nitrogens, and then we already looked at oxygen. So balanced atoms, then there's 3 minus 2 things. So minus 6 plus 2 more positives, and then 2 more negatives. So it looks like we got a minus 6 over here. And then we have 3 minus 2 things, so minus 6, neutral, neutral. So our charge is balanced as well. The reactant side is a minus 6, and the product side is a minus 6. Okay, everyone? Make sure that you finish the problem set for the redox reactions in an acidic solution. You will be happy that you got that done. Okay, I will see you all tomorrow. You're going to do awesome on the test.